Hello, can everyone hear me? Okay, great. So let's get started. So the topics for today we will be covering multiplexers, programmable logic devices, tri-state logic, flip-flops and latches, registers, and maybe near the end, let me know if you want me to cover Verilog using Vivado. And this topic I got from Dr. Balsara, and I believe this will all be on your exams. So let's dive into the first topic. And the definition for multiplexers is to select one of the multiple inputs to the output. And to take an example that 2-to-1 multiplexer is that we will have one selectors, and therefore we will be able to have two inputs. And this is the diagram for 2-to-1 multiplexers below, address 0 and address 1 with the selector, and this will be our output. So in your homework, I saw some problems using multiplexer to realize some functions, and in order to understand the fundamental of that, we will have to dive into the circuits inside the multiplexers. And for 2-to-1 multiplexer, we need an AND gate, and let's call this at address 0, and then another AND gate, and this will go to our output with the OR gate, and the second AND gate will take care of the input at address 1, and below we will have a selector, and this one will actually go into an inverter. So right here, this is basically what's inside our mux. So if we look at the Boolean equation at the output here, and assuming we have input A and input B here, we will see that the output from this AND gate is actually A S naught, and the output at this AND gate is B and S. So we know our output will be equal to AS naught or BS. So now take an example of the function, like let's say 3 input, X, Y, Z. And let's say we have X naught, Y, Z, or X, Y, Z naught, or X, Y naught, Z naught. So from this Boolean equation here, we can see that we might need to have, without simplifying this, we might need to have like two selectors multiplexers. Therefore, we will need a 4-to-1 multiplexers. So let's draw our mux here. We will have S0 as S1. And then therefore we will have 4 addresses, which means 4 inputs. So let's say if we choose YZ as our selectors, we will encounter some, actually we will not encounter problems here because YZ will be able to differentiate each of the term here. But let's say if we happen to have Y and Z not here, then we will encounter problem when choosing which term to pass through the output. We will end up having to use X naught or X and end it with Y Z naught or X Y naught Z naught. But there's actually a simpler way to do this, because if we choose YZ naught, we will have 2 terms that we need to take care of in the POS form. But if we choose X naught and Y, if we choose XY to be our selectors, we will be able to differentiate each term using just XY. So let's say we use YZ naught first as our selectors and put it here. We know when Y is 1 and Z is 0, this is going to be selecting address 2. And therefore we will need to have an OR gate. Well, but in this case it's just 1. Sorry, this is a bad example. Let's say X not Y not. Yeah, well, this will be simplified into 1, but without simplifying this, we will need an OR gate to realize this function here. But however, if we choose X and Y to be our selectors, we will see that XY will be able to separate each of the term. So when X is 0 and Y is 1, this is going to select address 1. And let's go with the initial value. So when this is 1 and 1, this will actually select address 3. When this is 1 and 0, this will select address 2. So if we look at each of the term here, we can just input Z naught at address 1 and Z naught at address 3 and Z naught at address 2. And for the addresses that are not in the Boolean equation, we just input 0. So therefore we will have an output here of X, Y with Z naught, or X, Y naught, Z naught as well, or X, Y, Z naught. And with this as our selectors. So let's take a look at a more complicated problem. So let's say we have Q, well, P equals to and we have Wx naught y or V naught Z naught or Wx naught y naught or Vc. So for this equation here, we have to do the Shannon expansion. To choose the best result for our boxes to use. And if we just use, let's say we use x and y as our selectors. We see that some of the term, well, for this term, we already know that it has x naught and y naught. But this term, the xy is missing, so we had to do the Shannon expansion of this. And about this one, there already are x and y, and for this we have to do a Shannon expansion. So to do this, we can apply the rule of the complementary. So let's do x first. So V naught Z naught will equal to V naught Z naught x or V naught Z naught x naught. And to prove that this concept works, we can see that V naught Z naught ended with x or x naught, and because this is just one, so this equal to this function here. And after doing this, we still need y for our selectors. So therefore, we have V naught Z naught x. Let's do this first. V naught Z naught x. We'll have V naught Z naught x y or V naught Z naught x naught. No, it's actually x and y naught. And we will have to do the same thing for this term, which is V naught Z naught x naught equal to Z naught x naught y or V naught Z naught x y naught. So after getting all these equations here, we can then plug these two into our V naught Z naught. And then therefore all of our term will have x naught and y. I mean x, y as to be our selectors. And for simplicity, I will just erase the last term there. So let's rewrite this. P V W X Y, I believe Z. So we will have W X naught Y ordered with these two, which are V naught Z naught X Y, Z naught X Y naught, X and Y naught. And then the last term will be W X naught Y naught. So let's go to our boxes. Because we chose X, Y to be our selectors, that means we will have a 4-to-1 multiplexers. S0, S1, X and Y. So let's see if we have any terms that share the same X and Y. So we can see that these two terms has both X0 and Y. So we can do W or B0 and end up with X0 and Y. So therefore, at this address here, we have X as our 0 and Y to be 1. So this is actually address 1. So we will have an input of W or V0 into address 1. And if address of 0, 1 is selected, then our output will be W or Y0. And for the next term, we have V0, Z0, XY. And we actually don't have any other terms that share the same XY. So at address XY, so this will translate it to 1, 1. Address 1, 1 will be address 3. So at address 3, we will only have V0 ended with Z. And let's go to our next term, which is X and XY0. And it actually shares the same term with this. So V0, C0, and 3 with XY0. And this here will be our 1, 0. So this is address 2. So our input will have B0, C0 here. And for address 0, we know that X, Y does not repeat in other terms. So at address 0, we will have W here. Okay, so far, does anyone have any question? Oh, I forgot the X. Where's the X? Yes, I think so. I'm not so sure how Vedant will handle this, but I think this review will be posted after it's done. Yeah, so someone said that I forgot X somewhere around here, but I hope you got the idea of how to approach this problem. So now that's done, we can redo. Oh, so previously we have the VZ as our last term, right? But for simplicity, I just expanded V0, Z0, and I figured it's better not to waste time to expand VZ again, so I didn't include the term VZ. So X. Let me see where I missed the X. Okay, V naught, Z naught, X naught. Oh, this one here? Sorry about this. So this will be X naught. Yes, I forgot this. So this will be X naught, and therefore we will need to Is this one what you're talking about? Yeah, thank you for pointing that out. So I forgot that's X naught there. So because there's some changes in this portion here, so we will have to change our Boolean equation accordingly. And let's say we have, so this is X naught here. So now this term actually shares the same X, Y with this term. So we will have to change this to X naught, Z naught, or W, and with it X naught, Y naught, and this is address 0, 0. So therefore we will have V naught, Z naught, or W at address 0, and for this term here we still have only VZ naught at address 2. So this stays the same. Yeah, thank you. And let's move on to how to make four higher inputs muxes using a lower input muxes. So what I meant is that using 2-to-1 mux, we will be able to create 4-to-1 and maybe even higher to 8-to-1 and so on. So initially we want to create a 4-to-1 using the 2-to-1 muxes. We know there are 4 inputs, therefore we will have 2 selectors, and this will be our output here. So how do we create it using just 2-to-1? So because we know that there are 4 inputs, and therefore we must use at least 2 mux at the beginning. To realize the 4 input we need. And however, at this location here, if we don't have another 2-to-1 mux connecting the initial 2, we will have 2 output here. This is output 0, and let's call this output 1. Therefore, we will need another 2-to-1 mux here. And selectors here, and we will have the selectors here. So what happens if we use S0 as our selectors here? Let's put the S1 and S0 here. So when S0 is 0, it will select this mux to pass through the output here, right? So therefore, if we select S0 to be at our selectors for the output mux, we will have to use S1 here. And S1 can be either 0 or 1, as well as our S0. So when S0 0 is 0, this mux will be selected, and the address here, if S1 is 0, the address at this location will be selected. And this is actually address 0. But if S1 is 1, we know 1 and 0 will give us 2. So this address will be selected, and we will call this address 2. And what happens if we put S0 as 1? We will pass the output 1 to our final mux here instead. So if we have S1 here, and when S1 is 0, we will have 0, 1, and this will actually be our address 1. However, when our S1 is 1, we will have 1, 1, and this will actually be our address 3. So to match the corresponding addresses, we have already labeled that this to be address 0, 2, and these two to be 1 and 3. And there's a simpler approach to this problem. If we set the higher mux to be as 1 and our two initial muxes to be as 0, we will actually have the addresses that match the initial 421 mux we have here. So let's, for example, we have S1 at 0, and therefore we will have our S0 to be either 0 or 1. So when S0 is 0, this address will be selected, and this will be our address 0. And when S0 equals to 1, this will be address 1. And address 1 will be selected to pass to the final mux. Now when S1 equals to 1, we know that this mux will be selected instead. And S0 can be either 0 or 1. And because we know 1, 0, it gives us 2, and 1, 1 it gives us 3. When S0 is 0, this address will be selected, and this will be our address 2. And when S0 is 1, this address will be selected, and this address will give us 3. So this is how you will create a 4-to-1 muxes using 2-to-1. And using 2-to-1, you can create higher input muxes like 8-to-1 and all the way to infinity. Anyone has any question? Okay. So we can move on to programmable logic devices. So the first type of programmable logic device, PLD, is PLA, and it follows the AND and OR structure. And both AND and OR are programmable, which means that the AND doesn't have to necessarily be a decoder. Well, I made the mistake during one of the tutoring, and I said that PLA has to follow the strictly decoder application for the AND structure, but instead that's for ROM instead. So assuming we have 3 inputs, and have function of A, B, C. And let's say we have A not B, C not, or A, B not, C, or A, B, C. And we can see that we can actually simplify this equation to A not B, C not, or AC. And let's say we call this F1, and let's say we have another output we need with the same input of A, B, C. And let's say we have A not B not C not, or AC. So when drawing the diagram for this PLA, we have to have an array of input. Let's say we have, usually we draw it as a line here. And we will also need an inverted for each input. And because the PLA follow the AND structure, AND OR structure, therefore we will need an AND gate to connect to the input, and then we will have the OR gate connect to the output of the AND gate for our output. So we see here we have, for F1 we have A not B, C not, and ORed with AC. So for F1 we will need at least 2 AND gate. And to connect this, we can simply draw a line across and use X to symbolize that there is a connection there. So the first term is A not B, C not. So we make connection A not B, C not. And in the actual physical world, this is actually not how it's connected. This is actually a 3 input AND gate, and each input of the AND gate will be connected to different variables input there. And we will see that the second term will be AC. So again, we draw a line across and state the connection here, A and C. So now we can move on to F2. We know F2 has like A not B not C not, ORed with AC. So without looking at the F1 output, we will know that we will need at least 2 AND gate. But however, for PLA, we can program the AND gate AND structure so that the AC here we will be able to share the same AND gate. So we only need a total of 3 AND gate. And because this is already AC, let me label this A naught B C naught. And this one will be our A naught B naught C naught. So we draw a connection here. So after we finish with the AND structure, we can move on to the OR. So what we're trying to do is to have 2 outputs of F1 and F2. So therefore we will have a maximum of 2 OR gate. Let's call this F1 and let's call this F2. And we basically do the same thing for the AND structure. We draw a line across. And for F1, we need to make a connection at A naught B C naught. So this portion here. And we also need to make a connection at AC. And for F2, we need to make a connection at A naught B naught C naught and another connection at AC. So PLA is pretty simple. And let's move on to ROM if there are no questions for this. Okay, so for ROM, we're still following the AND OR structure, but the decoder is used as the AND structure while the OR is programmable. So let's go over the decoder as a review. If we have a 2 input like AB decoder, we will have 4 output here. And this will be our LSB. And let's say this is our MSB. And 1 here. And this is our address 0, address 1, 2, and 3. And let's say we put let's put B as LSB. Let's put B here and A here. We know the output at address 0 will give us A naught B naught. And the output at address 1 will give us A naught B. And address 2 will give us A B naught. And at address 3 we will have AB. And let's use previous example of F1 and F2. So for this equation here, we know that we cannot have this term here because we are following the decoder format. if we want to use this term, we will have to expand this term using Shannon expansion. So AC will become ABC or AB not C, as well as this term will be the same as this one. So we have a total of 3 inputs. That means we will have a 3x8 decoder initially. Show this here. So 0, 1, 2. 2 means that this is MSB and this is OSB. And let's say we put A, B, C in this order. We will have 2 to the third. So this will give us 8 addressed line. So 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so from F1 and F2, after doing the Shannon expansion, we will have A not B, C not, or A B C, or A B not C. The same thing for F2, we will have A not, B not, C not, or A B C, or A B not C. And from this, we basically took care of the end structure of the ROM. And now we can move on to the OR structure. We basically follows the same procedure for PLA. We can draw a line across and connect to the output of the decoder. So as we can see here, F1 has connection at A not B C not. So it's address 2 because this one will give us 0, 1, 0. So this is 2. And this one will give us 7. This one will give us 5. So we have another connection at address 7 and another connection at address 5. So this will become our F1 output. And for F2, this is address 0, 7, and 5. So the only connection difference is that it's at 0 and 5 and 7. And we call this F2. And to call this, we know this is a 3x8 ROM because it has 3 inputs, therefore has 8 addresses. Well, actually, my mistake. This is 3x8 decoder. And we know for decoder, if we have 3 addresses, we will have 3 inputs, we will have 8 addresses. So this entire thing will become our 8 by 2 ROM. And I know some professor allows you to simplify this further into a format of lookup table. We still have this input A, B, C. And this is a different way to draw the ROM. We have 0, 1, 2, 3. And we will have two output, F1 and F2. So this is called the lookup table inside a component symbol. So we know that F1 has to output a 1 when our address 2 is selected, right? So that means ABC has to equal to 2. So F1 A, B, C equals to the sum of this is 2 and 5 and 7. For our F2, we will have 0, 5, and 7. And what we want to do here is basically fill out ones for F1 and F2 when there's a address that it should be output of 1. So at address 2, we know F1 should be 1. So at this occasion, we put a 1 here. And how about F2? Because F2 does not contain the minterm of 2, and it only has 0 instead, so we fill this in as 0. So let's go look at the 0 for our F2. And because F2 has the minterm of 0, so we will have 1 here. And F1 does not, so we will have 0 here. However, for 5 and 7, both of them shares the minterm. So we will have 1, 1, 1, 1 here, and 0 for the rest of other. Okay, so in one of your homework, you were asked to design the ROM, and that's going to calculate the trigonometry for you. And let's do a similar problem. Let's say we want to square the input ABC. This will be in binary first. So we know A, B, C. Give me a second. We can first start by drawing the truth table. We have A, B, C. So we want to go through all the possible value first, just like the truth table. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1 1 0 and 1 1 1. So what you can do is that you can get out your calculator, and we want to look at the minimum. So this, we know in decimal this is 0. This will be in 1 2 3 4 5 6 7. So the problem is asking us to square the input, right? So we can see that 0 square is still 0. 1 square will be 1. 2 square will be 4. 3 square will be 9. 4 square will be 16. 5 square will be 25. 6 square will be 36. 7 square will be 49. So we know we had to have a binary value of up to, let me see, so 2 to the 4, 2 to the 3, 2 to the 2, 2 to the first. We know this is 1, 2, 4, 8. And this, whoa, my mistake. So we have 2, 4, 8, 16, 32. So we need a maximum of 5 inputs, 5 outputs to realize our 49. So let's go up here, and our output column will have, let's say, output 5, output 4, 3, output 2, output 1. So we basically want to convert the decimal value here into binary. So 0 square is still 0 in binary, so this row here stays the same. Let me double. Okay. And 1 square will be 1, so still the same. This will be 0 0 0 0 1, and the next one will be 4, right? So we know down here we will have 0 0 0 1 0, right? Let me say something. Oh, I think I missed a 2 to 0 here, so this will be 1. Oh, 0. So 4 will give us 1 0 0. This is going to be, and this one will be 0 here. So 2 squared will be 0, 0, 0, 1, 0, 0. Yeah. And how about 9? We will have 1, 0, 0, 1. So 3 squared will be 0, 0, 1, 0, 0, 1. And then 16, we will have 0, 1, 0, 0, 0, 0. For 25, we will have 1, 1, 0, 0, 1. And for 36, we will have 1, 0, 0, 1, 0, 0. For 49, we'll have 1 and 1 here. This will be 48, 0, 0, 0, 1. Right. So we can know that because we have input of 3, therefore we will have a decoder. Let's do and 0, 1, 2, 3, 4, 5, 6, 7. And then we will have a total of 5, 6 OR gate because we have 6 output. So where are we going to connect for O5? Let's say we have O5 here, O4, O3, O2, O1, and O0. So we know O5 is 1 when address 6 is this one here. When address 6 is selected. Oh, sorry. And as well as address 7, right? So this row. So we know we have to make connection at address 6 and 7. And we do the same for all 4, which is address 4, 5, and 7. Address 4, 5, and 7. And then for output 3, we will have 3 and 5. At output 2, we will have 4 and 6. Wait. No, actually, at output 2, we will have 2 and 6. And then do the same thing for output 1 and output 0. So we actually don't have any connection for output 1. So we can discard this because we know OR structure is programmable. So we can get rid of the unnecessary gate. But for O0, we have address 1, address 3, address 5, address 7. So 1, 1, 3, 5, 7. 5 and 7. So this will be your 8 to 8 by 6 ROM. Because again, this will this is going to tell you the number of output. And this is the number of addresses. Oh, thank you for the reminder. I forgot 2 to the 0. Yes. Thank you so much. So any question for ROM? If there is no question, we can go to the tri-state logic next. And okay, let's go to the tri-state. So the symbol for tri-state is below as shown. So we will have an input at the side, and kind of like the inverter without the invert. Okay. And this will normally be used as our output here, and this is normally our input. And normally we can call this as our select, and I can explain why later. So in order to understand this, we have to have a truth table. So let's say this is input. Let's say this is the input A, and this is the input B, and output will be our C. And drawing the truth table A, B, C. We know we have 0, 0 first, 0, 1, 1, 0, and 1, 1, right? So the tri-state, you can actually write this as A going into a switch, and then B, when B is 0, they will be open, and when B is 1, the switch will be closed. So that means that whenever B is 1, whenever B is 0, looking at from the output C here, we will have high impedance at this location as well as this location. However, when B is 1, that means the switch is closed. So A will pass 0 to C, pass 0 to C, and in this case A is 1, and we will have 1 here. So this is pretty simple, the tri-state logic. And another fun thing to take care of is that we can actually use this as our multiplexer. Because using the truth table above, let's say we have two tri-state, and the output are connected, and we can put an invert sign here, so this symbolizes that the input going into the tri-state will be inverted. And let's say we have non-inverted. And let's call this S and call this XY. And when S is equal to 0, 0 is going to close this, open the switch of this tri-state here. So we will have high impedance here. See? However, 0 going to the inverted input, we will have a closed switch. So this will actually output an X. So our output will be equal to X when S is equal to 0. However, when we switch the input of S, let's say we have S equal to 1. Now, the top tri-state will have high impedance, and the bottom tri-state will have Y going out of the output. So when S is equal to 1, output equals to Y. And therefore we can derive a Boolean equation saying that X is not equal, X is not or Y is. So we can see this is actually our two-to-one mux. The output at this location F is also equal to X S naught or Y S. Any questions so far? We can move on to the next one if there is no question. Okay, so because your professor told me that flip-flops and latches will be on your exam as well, so I should cover that briefly. So the flip-flops is defined as edge sensitive and usually driven by a clock. And by edge sensitive, it means that the triggers either on the falling edge, either the rising edge or the falling edge here. And for latches, it means that it's level sensitive. So either it's triggered at 0 or it's triggered at 1. And right here we have a circuit diagram for our SR latch, and we can see that it's built using the NAND gate. So we have our truth table right here. So let's try to fill out the truth table for the SR latch. So the key to this is that whenever there's a 0 as our input into the NAND gate, we know the output will for sure be 1. So let's look at this row here. The 0 row. Yeah, so whenever there's a 0 input into the NAND gate, we know the output will be 1. So we know for sure that this one will be 1. This one will be 1. Well, actually this one will be 0, right? Because assuming that previously we have 0 here, and well, this is storage. I apologize. So when this is initially we have the 0 and 1 as our Q and Q not there, we know this will pass 0 to this our NAND gate here. So we know this will for sure be 1. However, when Q naught is 1 and it passed through this portion here, this state is undefined until we define the S. So for 0, 0, okay, so when there's 0, 0 input into SR latch, we actually got a undefined value, because we want Q to always equal to Q naught. So when S is 0 and R is 0, that means all of our NAND gate will output a 1 here. But if Q is 1, then we want to expect Q naught to be 0. So we can state this state as undefined. And then we can move on to the next state. So let's say R is 1 and S is 0. So for this case, we have 0 going into our S input. And we know whenever there's a 0 going into the NAND gate, the output of the NAND gate will always be 1. So in this case, our Q will be 1. And then Q is 1, so going into the bottom NAND gate, we will have 1, 1. And looking at the truth table here, we know the output will be 0 from the NAND gate when both inputs are 1. So we know Q naught will be 0. And then we can move on to the next one. So whenever S is 1 and R is 0, we know R will for sure, the output of Q naught will for sure be equal to 1. And therefore this will be 0. So right here we actually have 0 as our Q. So 1 going into the top NAND gate, we will have 1, 1, and then therefore our Q will for sure be 0. Going to the next one, which is S and R, when they are both 1. And looking at the truth table here, we have to depend on the value of Q and Q naught, because 1 does not determine whether it's 0 or whether it's 1. So it's dependent on the previous result. So let's say if we initially have Q at 1 and Q naught at 0. And looking at Q naught first, 0 will pass through the NAND gate. And therefore 1 0 into the NAND gate will for sure give us a 1. So our Q will be 1, stays the same. And if we use previous value as Q equals to 0 and this as 1, then looking at Q naught again, we will have 1 1 pass through the NAND gate here, and our Q will become 0, not become 0, it stays 0. So this is store. And I believe most of your homework problem uses the NOR gate. And let's do S here, R here. So we can follow the same procedure, but instead of using a truth table for NAND 2, we can use NOR 2. So this here will be 1, and the rest will be 0 for NOR gate. So we can see here that the 1s actually determine whether the output can be 0 or not. So let's do the table where there are 1s here first. So we initially will have S at 0 and R at 1, right? So we know for sure 1 going into the NOR gate here will for sure give us 0, right? And then 0 going to the top of the NOR gate. 0 0 is going to give us 1. So we know in this case it's going to set, so Q equals to 1. And let's say we have S as 1 next and R as 0. We will have Q to be 0. Oh, what did I do? And however, if we do 1 1 for both S and R, we will actually get 0 at both of our output Q and Q naught. So this will be our undefined state. And this will be our storage if we follow the same procedure we did for the NAND SR latch. So we can see that we have some problems for undefined when we only use 2 NAND and NAND or NOR. So other flip-flops is derived. This is the top here, the top 2 here are called the SR latch. That means it's not driven by any clock, it's just driven by S and R. And right here we have the JK. Well, technically this is a latch as well, but there's no JK latch. I never heard such thing as JK latch because it's still going to be level sensitive, although we have a clock here. So I recommend you to memorize this. And let's draw the truth table for JK, Q, and Q. Let's just do Q. We have 0, 0, 0, 1, 1, 0, and 1, 1. So the truth table for JK flip-flop is going to be 0, 0 is going to be store. 0, 1 is going to be the reset. Therefore, our Q will become 0. And when J is 1, K is 0, this is actually our set. So Q will be 1. However, when J and K are both 1, then we will have toggle. So if previously we have Q at 0, then when the clock goes from when the clock is at high level, we will actually get 1. But this still has some flaws here. Although it said that it's toggle here, because it is level sensitive. So at this point here, it will toggle continuously until it drops down to the low level. So what it means that when the high level is detected, when clock is high, it will keep toggling non-stop due to the propagation delay of gates. So to solve this problem, we can actually go to the master-slave flip-flop. And this will be our input J and K. So what this gives us is that we can only have our input changes at either rising edge or falling edge. So this is a true flip-flop here. If we use J and K to be our input, we can observe the same thing happening with the previous truth table we drew. And Q. So this will be our storage. And this will be our toggle. And this time, it will not keep toggling when the clock stays high or low. It will only toggle when the clock is going from low to high or high to low. And this will be reset. So Q equals to 0, Q equals to 1, this is set. And we call this a master-slave flip-flop. And by doing so, we can improve the previous design and make it a edge trigger, either falling edge or rising edge. And falling edge means that it's going from high to low, and rising edge is going from low to high. And we also call the JK flip-flop as our universal flip-flop because there are a total of T flip-flop, and T stands for toggle. We have delay flip-flop. Delay means, D flip-flop means, the D means it's delay. and it can also be SR, set and reset, because of the J and K function. So when J and K are not connected to anything, we can just say it's an SR flip-flop. So how do we make a D flip-flop? If we go back and look at J and K here, we will see that J and K, when J and K are 0 and 1, it's reset, right? So basically what it means that we can connect an inverter, connect to K, and then share the same input of D. So when D is 0, that means it reset, right? So the definition for D flip-flop is that whenever the clock triggers, our output Q must equal to our input D. For example, if initially Q initial equals to 0 and our D is 1, after the clock triggers, Q will become 1. And same thing for when Q is equal to 1, D is equal to 1, then our Q next will still be 1. And the same thing for the other. So using the D flip-flop, this is our input D, and this is connected to the clock. So basically Q equals to D when clock becomes D when clock trigger. And there's another flip-flop called the T flip-flop, which is toggle. We basically just connect JK clock. We basically connect J and K together and call this T, Q naught. So when T is 0, J and K is at the storage state. When T is equal to 1, both J and K are 1. So when it's 1, 1, it will toggle. Q equals to Q naught when T is 1. However, Q stays the same when T is 0. Okay, so after we have the D flip-flop, we can go to a really common register. It's called the shift register. So we use D, the value D here. To perform the shift function. So let's have a timing diagram. Let's call this D0 and this is D1. So at D0 and this is D1, and we will have Q0 and Q1. And we'll have a clock. And assuming our D flip-flops are rising edge trigger, and assuming that initially we have value of Q0 and Q1 at 0 as well. So let's say initially we have D0 at high input, and the rest will be 0. So when the clock ticks, our Q0, because Q0 is this flip-flop right here, our output of Q0 will actually go to 1. And then until the next clock pulses. So how about Q1? Because previously we know Q0 is at 0, and we know Q0 is going into D1. So we know this will be this. So our Q1 will stay 0. And when the next clock pulses again, we want to check D0. D0 is at 0 at this location. So our Q0 will actually go back down to 0. How about our Q1? Our Q1 is going to, we need to look at our D1. We know previously it's at 1 because of Q0. So this will now go to 1. And then eventually this will all go to 0 because D0 doesn't have any input anymore. So the sequence of this is actually Q0, Q1 sequence. It's actually 0, 0 to 1, 0 to 0, 1, and then back to 0, 0, which is back to this portion. So then in your homework you have register, right? And what we have here, this is the 2-bit should register. And let's do a similar question. So you want to have a processor designer that's working on the shifting pattern. let's say, because I cannot do the homework for, let's say we want to design a processor and with a shift register. That can shift in both directions. So how do I do this? Is that, let's say we have a 3-bit shift register. Therefore, we know we need at least 3 flip-flop. Let's call this D. And the other flip-flop. And this is D0, D1, D2. So if we connect this like we did in the previous problem, we know that when the clock pulses, it's always going to be shifting right. It's going to be shifting in this direction. But the problem asks us to design a shift register that can shift in both directions. So what we can do is, let me try this down. We can use a multiplexer. We have, and to determine what how many selectors we need, we have to go to the problem and see how many instructions it wants us to perform. So it only asks us to do 2 operations. So one operation will be, let's say, shift right, and the other operation will be shift left. So in this case, we only need 1 selectors. Actually, let's put the selectors above at this location. And because we only have 1 selector, we can only select 2 addresses. Okay, so let's set instruction at s equal to 0. Instruction 0 is shift right. And we know at s equal to 0, we're selecting this address, right? So connect Q to our address 0, and the output of this mux will be connected to the input of D1. So we need another mux here. 0 and 1 selector. S. And because we said that the instruction when s equal to 0, we want to shift right. So we connect this address 0 to the previous D flip-flop, and then the output of the mux will be connected to the input of the next one to the right of our D flip-flop. So as we can see here, if we set our S to be 0 and D here, and this is our output here, we can actually see that the value will be shifted right for each clock pulses. So we can take care of, we took care of a shift right function. So now we want to shift left. Actually, this will actually be our input 2. And input 1. So what can we do if we want to shift left? We can input a 1 for this. And then in order for this, the value of Q2 go to Q1, we have to connect Q2. Oh, wait. Give me a second. Sorry. So when 1 is selected, then okay, yes. So when 1 is selected, we have Q here, right? So and we want to pass Q2, the value of Q2 to our D1. So what we can do is, this is a bit messy. We can connect the value of Q2 to our mux input here. Right. And then our Q1 will have to shift left. So we actually need another multiplexer here if we want to perform two operation. So 0, 1, S. We want to connect this portion to our input address at 1, and this will be connected to this portion. and this will be our input 0 when we are shifting right, and this will be our input 1 when we want to shift left. Sorry, this diagram is a bit messy. Let me do it again. Let me redraw this and let me know if you have any question. Any questions so far? So this will be our input 1, and this will actually be our input 2. Let's shift left, and this will actually be connected to this, while this will be connected to this, with all the same selector. So for this circuit here, we can see that when S is equal to 0, we're going to take this input going into D, let's call this D0, D1, and D2. Input 1 is going into D0, and then D0, when the clock pulse, is going to pass to Q, and then Q is going to go to the mux here at address 0, and knowing that S is 0, Q0 will pass through D1, and then D1 therefore will pass through Q1, and so on. And if we have S equal to 1, then we know input 2 will be selected, and input 2 will pass through D2, therefore pass through Q2, and Q2 will pass through the address 1 of this selector, and then this will pass to D1, and then D1 will pass through Q1. Q1 will go to this mux again, and then it will pass through Q0. So we can see that 0 is shift right and 1 is shift left. Does this make sense? A bit. So is there any question you have for this problem? Or do you want to do more problem for this? Okay, sure. So okay, let me see. There's actually a program on this topic. Let me see if I can open this. Okay, so let's say we have a processor and we want to perform 2 operations. So the first operation we want it to be able to, first operation we want it to be able to store the value desired value. Second operation, we want it to shift right. So again, because we only have 2 operations, therefore we only need a 2-to-1 mux for our selector. We only need 1. And let's do 3-bit again. So let's say we are provided with 3 D flip-flop. Copy this. I should have done this in the beginning. It's much cleaner. So we have D. Oh. So we have D. Let's call this D0, D1, D2, Let's call this Q0, Q1, Q2. And they're all driven by the same clock. And because we need to perform two operations, so the D will be determined, will determine the value of our Q. So therefore we will need a box here. Okay, so this is our address 0 and 1 with our selector down below. And the output of the mux here will be, let's call this M0, will be going to the D0. And we will need 3 muxes because there are 3 bits. Call this M1, and this will be our M2. So before, because we need to perform two operations, so we want to select the instruction bit for our operation. Let's say to store the desired value, we set this at s equal to 0. And for the second operation, we set this for s equal to 1 for our shift right operation. So let's connect all the selectors together. So when s is equal to 0, we know the addresses are selected at 0. And for this, we want to store the value in there, right? For first operation, we want to store the desired value. So what we can do is that we can have input 0, input 1, and input 2. So when s equal to 0 and the clock goes from, let's assume the D flip-flop is active edge triggered. So that means going from low to high trigger. So when the clock triggers, then our Q0 will be equal to D0, right? Q1 will equal to D1. And Q2 will equal to D2. And we also know that D0 is connected to the output of M0. And when s equal to 0, that means input 0 is selected. So when the clock trigger, the value of Q will become our desired value. So this took care of the first operation. Now we want to perform the second operation. So that's when s equal to 1. So we know the second operation is going to shift right. So that means Q1 will Q0, Q1, Q2. Its value will shift right in this direction. So what we can do in this case is that when the clock triggers, we want Q0 to go to D1. So that means we'll connect this to Q1. Now we will have another input here. And depending on the application, maybe we want it to circle back to the previous, circle the last value into our first value. This is, I believe this is called the ring shift register. And we can also just put a desired value, let's say input 3. So when the clock is triggered, Q1 will be equal to Q2, Q0, and Q2 will be equal to Q1. And Q0 will equal to int3. Does this make sense now? So I believe you will be able to apply this knowledge to your homework problem number 2 on your homework 5. And the next part is going to be related to this, but it's going to be coded in Verilog instead. My pleasure. So I want to show you the Verilog just to show you what the timing diagram looks like. And maybe on the exam you will be asked to draw a timing diagram. So this is the code. So basically it's a sequential detector plus a shift register. So when a certain sequence is detected, it will decide to shift right, or maybe the next sequence is detected, it will shift left. So if we run the elaborate design, we will see that it can generate a schematic for us. Sorry, it's really slow. So basically, it will convert your Verilog code into a schematic, like a physical component. Just need to wait for it to load. So as you can see here, we have some AND gate. It's used for the sequential detector, and we have some muxes connect to the input of the D flip-flops, just like the one we did. And each D flip-flop has one mux corresponding to it. And if we run the simulation for this schematic here, you will see that it actually has a timing diagram. Let's go to simulation source. Run behavioral simulation. Oh, what did I do? Okay. This is awkward. Come. Okay, so apparently it doesn't work now, but I will show you the so basically if once we run the simulation, we will get a waveform like this, and it will tell you when the clock triggers, and then the value will change. So for example, this is a shift register, right? So our system input is going to be going into our first flip-flop. Let's say it's D1. So when the clock is rising from 0 to 1, we can see that there's the value of system input will shift to the right. So we will get from 000 to 100. And then because the system input is set to 0 for the rest of the case, so when clock is triggered, our Q0 will shift to Q2 and Q1. Q0 will shift to Q1, and so on. And there will be some sequential element, sequential detector incorporated in this design. So this is just to show you what the timing diagram looks like for shift register. Okay, so that will be all. Is there any more question? Okay, thank you so much for joining for this test review, and I hope you do well on your exams. And please let me know if you have any more questions. You can either go to the Discord tutoring channel to let me know, or maybe some other time you can email me. Good luck.